All right, so our tutorial for today is a work into moderated mediation. This video is just going to cover mediation in R with bootstrapping. And we'll compare our results that we get to the very popular plugin in SPSS that is programmed by Andrew Hayes, the process plugin. And so if I look at my channel, I think the most popular thing that I have is using the process plugin, the different models in SPSS. And I've really tried to find a way to move people to R and not rely so much on SPSS, which I very rarely open anymore. And so what I'm going to do here is take some data I had when I did a video for Model 7 of moderated mediation and work on showing you how mediation works, with sort of part 2 being how you can modify these mediation scripts to do moderated mediation. This is also going to help with an analysis we're running in our lab, so double usefulness. So we're going to start by importing the data, and I actually have this as an SPSS file, so .save, and just to give you a warning that the new Haven library that's part of import. So if you want to use import dataset from SPSS, that's essentially what this code does. It is fantastic. It's a great new component to RStudio. However, the new CSV import sucks. So don't use the CSV one. Use the base R version, which is read.csv, not read_CSV. I've had so many problems with it. But Haven's read_save is actually really great. So I'm going to open that library and set my working directory to where I have all this stuff hidden and import that file as my master file. So I'll walk through a little bit of data screening here. So I'm going to screen this as I would if it were an ANOVA. So I'm going to use my fake regression style data screening, which you can learn more about if you watch my data screening videos. And what that'll do is it'll allow me to screen across all of the variables. And so I'm actually going to screen here for the moderator, even though we're not going to use it in this analysis, because part 2 we will use it. So I'm going to screen for all the variables. If you're doing just mediation, be sure you screen the mediation model, and you could do data screening on this sort of B-path model that includes X and the mediator predicting Y, and look at the regression output from that and use data screening from that. That will work as well. So kind of either way, this way will allow me to screen all the variables I'm going to use eventually. So let's look at accuracy first. So I'm going to take a summary of that data set. And so what my data set has in it, it has a random variable in it, but I'm not going to use it for this analysis. It's left over from an SPSS video. But what I have some sort of X variable, mediator variable here, M, a moderator variable W, and you'll notice this matches the process style naming, and some sort of dependent variable Y. And so we think that X predicts Y, and it's mediated by M, and then that W variable moderates that mediation relationship. Okay. So first thing I'm going to do is actually just ditch my random column, so I'm not using it. If I wanted to look at the accuracy, though, before I forget, is this everything in this data set should be a 1 to 5. Because this was average faculty evaluation scores that I sort of am using to show some other examples. And everything looks like it's 1 to 5 using my min column here and my max. So I don't have any typos. I don't have any missing data because you would be able to see missing data in that summary. So let me work on outliers. So remember, Mahalanobis does not work on categorical variables, but we don't have any of those here. So I'm going to do Mahalanobis. First piece is the name of the data set, comma, call means, which calculates the average for each column, the name of the data set. Co for the covariance matrix between columns, which is why I like using Mahalanobis, because it accounts for the fact that columns are related. And the data set name. So we're going to save those as Mahal. So we have a whole bunch of Mahalanobis values for our data set. So this data set's really large, it's about 3,600 lines. Now I have to calculate a cutoff score for that. So the cutoff score here, I'm going to use q chi-square, is going to be 1 minus alpha. And so what we want to do here is calculate a cutoff score that is at the top of the distribution, because this is chi-square, and is in the 999th percentile, or 99.9th percentile, Jesus. And so we don't want to use 0.001 here, because that would give us the very bottom of the distribution and everything would be an outlier. So we're calculating at the top, which is why it's 1 minus alpha. I'm using 0.001 because of my big important rule, which if you've watched my videos, you've heard me say too many times now, where I want to make sure that the outliers are really, really wonky before I exclude them. This matches using a z-score of 3, which is approximately 0.001 p-value. So this here is the percentile that we're gonna find that cutoff score. And then this is the degrees of freedom for that percentile, and it's the number of columns that you put into the Mahalanobis. So we had 4 variables here, so it would be 4 for x, y, m, and w. But I can use this little code here to just do the number of columns that I used in the data set here, so I don't even have to think about how many it is. Here I'm going to create a table of the number of people who are less than the cutoff. So we want people's scores to be less than that cutoff score, because that implies that they are not an outlier when their score is less than the cutoff, which is a good thing. And so I have 3,500 people who are less than the cutoff and 58 scores that are above that cutoff. So I could say I had 58 outliers in this example. So I'm going to create a data set called no-out that is the non-outliers. And to prove that I didn't do this incorrectly, because it is easy to make a mistake, the number of rows in my new no-out data set should match the number of true values here. Now I can look at additivity, but one of the purposes of mediation is actually to check sort of for multicollinearity, not really multicollinearity, but you know, suppression, or to sort of, you expect there to be some correlations between the variables. But we want to make sure they're not too high so that our analysis doesn't go bonk. So I'm going to save that correlation table, so core, no typos here. I can output the correlation table because it's kind of small, and we do have some very highly correlated variables, which we expect because of the type of analysis we're doing. But remember, you can use that symbols for numbers table to make sure there are no stars or B's. Those are when you start to approach too highly correlated. Now that I'm okay with those, I'm going to do my assumptions. So I'm going to set this up by creating a random column, which I know I deleted my random column earlier, but it's from SPSS and it's not truly random, so we're going to create our own separate random column here. I need it to be the same number of rows as my data set. And 7 is just a magic number. There's no particular reason for 7 degrees of freedom here. I have used it for a long time. It's not even my favorite number. It's just the number that works. You can use any number greater than 2. 2 and 1 give you not enough variance, and 0 and negatives will blow this up. So pick your favorite number. That creates me a random column to work with. I'm going to run a fake regression where I predict my random variable that I just made with the entire data set. And what that does is it allows me to test if the residuals are random and evenly spaced. So we're going to get into normality and linearity using this random variable we just made. And there's a very long description on why that is a thing. And I'm doing this from the Tabachnik and Fidel book. And you can, if you watch the data screening videos, you will hear all about why should we predict a random variable. I'm going to standardize or studentize my residuals. And then I'm going to create my predictive values, and I'm going to scale those. The only reason that you really want to scale or z-score those is so that the graphs are easier to interpret. So now I've got everything set up. I've got my residuals, I've got my predictive values. Let's look at how linear those are. This should say linearity. Good grief. Okay. And so I'm going to add an AV line of 0, 1 just to give us a nice way to interpret. And generally you want to look between 2 and 2. Much past 2, then these are z-scores at the bottom. Much past 2, it's going to be hard to predict. And this is a little curvilinear. And so this data set is a hot mess. It is very problematic. So in reality, I should be doing some non-linear, non-parametric regressions on these, but for purposes of showing you how to do regular mediation, we won't. But with the warning that this is a little problematic, especially because it curves away from the line. Just wait till you see the residuals plot. It's really, really awesome. My histogram of my standardized residuals should be centered over 0, and it is, mostly between 2 and 2. I had a little bit of skew out here. Got this 1/6 I should probably check out, but mostly okay. Normality is an assumption that as long as we have at least 30 cases, we can kind of let the central limit theorem kick in. We have 3,500, so not as big of a problem, but it is a little skewed. This plot's going to be really awful, so get excited. So it's a plot of our fitted values. So these are our predicted scores against our standardized residuals. So the z-scoring was just to make this easier to interpret. I'm going to add 2 lines on those just to get it to be easier to read. And you want this to be evenly across 0 this way and evenly across 0 this way. Oh man, no it's not. It runs from 2 to 6. So that's why I said it's a hot mess. The bottom is okay for homogeneity. For homoscedasticity, you want an even spread all the way across. And actually isn't too bad, except for the fact that there's a higher concentration of data here in the middle. So not a great plot. But we already know faculty evaluations are kind of a hot mess, so proof. Now, if this were real data that I was really doing something with, I'd probably stop and try some nonlinear or non-parametric designs, maybe using the RFit package, because you could still do all these steps using that package. But for purposes of teaching, we're going to keep going with linear models. All right, so mediation, my first warning about mediation. So the original rules of mediation kind of argued that you should have where the x variable predicts y or else stop. And I'm still kind of that opinion that if I'm going to talk about mediation in its like normal interpretation where the addition of the mediator variable lessens the relationship between x and y, or somehow changes the relationship between x and y, I kind of think x and y need to be related first. So if I'm talking about mediation as the change from an x and y with the mediator versus without the mediator, it seems a little weird to me to say, well, it doesn't need to really be related in the first place. If I'm talking about mediation as the path of x leads to m leads to y, then I don't need x to predict y. So it kind of depends, I feel like, this question of does the C path need to be significant in the beginning, depends on the way that you think about mediation. So if I think about it as it changes or lessens the relationship between x and y, so x was related and now that you throw m in there, it's not anymore, then you need C to be significant or at least something interesting. If you're thinking about it as the relationship is actually x to m to y, you're talking about a path of x leads to m, which leads to y. Maybe x doesn't lead directly to y, but there's this third thing in the middle. Then maybe C doesn't need to be significant. So it's kind of, I'm going to show it to you with where C is important. If you're of the other camp that thinks C doesn't really matter, cool. You don't need this step. So generally, in the traditional steps, we first have x predicting y. So I've just called this the C path because that's its traditional name. I'm using LM for linear models, and I say y is predicted by x, and I've got my no-out data set. And what we find is that x does predict y. In this particular scenario, fairly big predictor if you consider that the scale is 1 to 5. I'm going to leave this unstandardized because traditionally people talk about the unstandardized coefficients. Next, we need to show that x predicts m, And I think either way, you really need x to predict m, because if a is not significant, you can't say that x leads to m leads to y. And so I've just changed this y here to an m. And x does predict m in our scenario. Now, when we get into the b and c prime paths, we're going to put x and m in the equation together and see what happens to each one. So we need m to predict y, and x maybe shouldn't predict y here, or it should be smaller, closer to 0. Okay. If x gets bigger when you put m into the equation, you might think about moderation interactions rather than mediation, with the proper theory behind it. And so looking at these, x has decreased from 0.6 to 0.1. So c prime does appear to have gone down. And m here is a nice big strong predictor of y. So we seem to have all the right things in place. But what we can do is, if you're a fan of the Sobel test, this is the same Sobel test that you might find in Process or on Preacher's website, quantpsych.org. What we're going to do is we're going to pull that A path from our saved linear model. This is why we saved them. I'm going to pull the B path. So what it's doing is pulling 1.03 here. And the A path is 0.49. I'm going to pull those standard errors from A and B as well. And those are here. So they're very small in this case because we have a very large sample. Scroll up a little bit. And here. And the nice thing about doing it this way, by saving it as code, is as long as you've saved everything in the previous steps as the same name, so this should continue to work no matter what you sort of change out for your variables. This sort of nasty formula is A times B, which is the indirect path, divided by kind of a weighted standard error. And this gives us a ridiculous z-score of 19, because this example is sort of made up to make this work. And so that is clearly going to be a very big z-score, and it gives us a p-value of -83. If you don't like scientific notation, you can use options. SciPin equals 999, which is turn it off. And we can see that that z-score has a very, very small p-value. Okay. So I'd argue that this shows mediation. I'm not going to talk about full or partial mediation. This shows mediation. However, if you're a big fan of the process model, maybe you want to also talk about the confidence interval. Now, confidence intervals on all of these values are basically 2 times standard error plus a minus, because my sample size is so large. But effectively, you could calculate those from the output you get in the linear model. Confidence intervals for the mediation effect or the indirect effect a little bit different. So what we're going to do is I'm going to kind of make this look like the process output. Okay. So I'm going to calculate my total effect, which is the C path, my direct effect, which is the C prime path, and my indirect effect, which is A times B paths, which we saved up here. Okay. That note does not need to go anywhere. Okay, I'm going to output those. So my total effect is 0.62, my direct effect is 0.11, and my indirect effect is 0.50. Now, in a very simple mediation, A times B is the same thing as subtracting C minus C prime. That is not true for any of the other craziness, because there are multiple other things going on. So if you can remember, the indirect effect is A times B in some form of that measure, you'll be better off. And so what happens in the process model is that there's a bootstrap confidence interval. And so what I've done here is programmed that bootstrapping to create the same confidence interval. And we'll test it here in a minute against process. And so bootstrapping, got to learn something new, how to use the boot function. God bless the internet for having tutorials. And the first thing you have to do is basically write your own little function, don't be scared, to calculate whatever you're interested in. And so what I've done is I have created a little function, so I've called it indirect saved. And the function has, the first thing it needs to have is the name of the data set or a placeholder for data set here. So I've just called it data set. And where you want to randomize. So what is bootstrapping? So bootstrapping is essentially the easiest way to think about this is the lottery. And so what happens is you have a whole bunch of balls. And you pull out one of the balls and you say the first number is 4. But in bootstrapping, you put that ball back. And you draw out another ball. The second number is 8. You put the ball back. And so you sort of pull randomly from your data set with replacement. So one person can be drawn several times. This is not the same thing as a randomization test where I scramble the data set. This is sampling with replacement. But you have to tell it what you want to sample, essentially. And so what I've done is I've saved that data set and I've told it to sample or randomize by row because I put it here on the first row. You could tell it to randomly sample by column too, but that doesn't make as much sense. So generally it's stuck here in the row function. Then I'm telling it to run the A and B path. Ooh, there's a typo here. Let's fix that. Should both be D. So to run A and B on our randomized data set, and if you don't run them on the bootstrapped randomized data set, you will get the same answer every single time, which is what God bless the internet, because that's what I was doing when I first got started. So I'm running A and B paths here, and I'm saving the indirect, and I tell it at the end to return that indirect. So it's going to return the whole list of those indirects, so how many ever times I want to run it. And I think this is the hardest part. The boot function itself is not so difficult. The hardest part was me figuring out where the random thing went, and how to have it return what I was interested in saving. Okay. All right, from there, this is in the boot library. Let me run this. I could, in the boot library, which is in base R, so I already have that on my computer, but you may need it. I'm going to use the boot function. The first command is, our argument is data equals no. In this case, I want to use my no out data set. I could change this to be my master data set or some other data set if I wanted. Statistic equals, and I put in the name of the function that I just wrote. And then R equals, and then the number of times I want to run this. The default, I think it processes 5,000. I'm only doing 1,000 so my computer doesn't blow up. But you can do as many as you'd like. You can do 10, you can do 2,000, whatever number you'd like here. Okay, so we're going to give that a second to run. All right, so it's done down here. I can look at my results, and results will give me the statistic here. So this is the same thing as my indirect effect, right? And then it tells me the bias and the standard error of that, but I'm actually more interested in my confidence interval. So to get my confidence interval, I do boot.ci of the results that I just got. I want a 95% confidence interval. You can change that to whatever you'd like. And I want normal confidence intervals. There are more options under type to see those. You do question mark boot.ci, and you can look at the bunch of different types of confidence intervals you'd like. I'm going to go with normal. That seems easiest. So it tells me that my 95% normal confidence interval is 0.47 to 0.55. Okay. And so that's about plus or minus 3 on each side. And that clearly does not cross 0. So I would say this mediation effect does not cross 0, which implies that it is a thing. Okay. I could say it's significant because the Sobel test is significance. I know the Sobel test is sort of losing influence because we have the ability to do these bootstrap confidence intervals, and they kind of will tell you the same thing. Okay. So we've got a nice big mediation effect here. Now, how does this compare to what everyone is in love with, the plugin in SPSS? So let me open SPSS. And one thing I'm going to do is because I've taken outliers out of this data set, I'm just going to write out my no out data set to a comma delimited value file. Yeah. And we're going to open that file here and import it real quick. So I'm going to do file, open data. Now I have to remember where the heck I saved it. Here. And we want to open CSV files. There we go. Oh, it wrote out the row names. I forget that R does that. Yeah. Good grief. All right. So now I have my data set, my no out data set, because I did my data screening in R. And so this should match fairly close. Okay. So to do the process plugin, I'm going to click Analyze, Regression, Process. That's why I named these variables the way I did. So I've got X in my independent variable, M in my M variables, Y in my Y. It's going to do a 5,000 bootstrap sample, which is pretty close. We'll leave this as bias corrected. And then model number is going to be 4 for mediation here. So I'll show you I'm using 2.16 of my plugin. I know there's a fairly new version of the plugin coming out either soon or it already has, but I think our numbers should still match. Under options, I could pick heteroscedasticity consistent standard errors, which is what I normally tell people to do. I don't have the effect sizes programmed in my little plugin, so I'm just going to pick Sobel, total effect models, compare indirect and direct effects. And I don't have any categorical variables. So I'm going to hit OK. I'm going to wait while my computer thinks very hard about that. There it goes. Okay, so we could compare the exact paths here, but I promise you they're the same. If I want to look at my total effect, so 0.62, come over here to R, just rerun this right here. Okay. 0.62107, this number over here, 0.6211. So they're exactly the same. My direct effect, 1114, come over here, 1114. So thankfully, linear math is still the same. Let's look at our indirect effect here, 0.5096. 0.5096, great. Let's look at our Sobel test. Now, this I have not gotten to match totally the same. So I think we're doing slightly different versions of Sobel. But here the effect is the same. The standard error is actually the same as well. It's just the z-score, we're doing different forms. So this is the Sobel test. We took the formula directly from Preacher's website, and this must be slightly different math, but they make the same argument. But since people aren't so happy with Sobel, let's look at how my confidence interval matches here. So I got 0.4707. The confidence interval here is 0.4691. 0.5495 to 0.5510. Now, very subtle, small differences here between those confidence intervals, bootstrapped confidence intervals, and I think if I had run mine 5,000 times, they'd be even closer. I just didn't want this video to take several hours. And so you can tell that by using this boot function here, I can get a fairly accurate 95% confidence interval on my mediation indirect effect in a way that is, I think, a little more efficient than using SPSS. There's nothing wrong with the plugin. I really love the process plugin. I just don't love SPSS. And so this might be a way, if you're an R person, to mimic those results and get a bootstrapped confidence interval, which leads me to the next video is going to cover how to do moderated mediation. The example I've programmed is actually model 5 from process, but you can take the next video and use it to program a bunch of different types of moderated mediation. So this is kind of leading into that. It's kind of part 1 of a 2-part series on mediation, moderation, moderated mediation with bootstrapped confidence intervals in R.